So let's talk through that. What did we say were our approximations or our simplifications for drawing structures? Every point is a carbon, so I'll do it in red. That dot is a point. So that is, by definition, a carbon. Carbon should have 4 bonds. I only see 1 bond. That doesn't mean it's not carbon. That just means what else?
There's something not there.
What'd you say? There's implied hydrogens. Okay? This is one of the big challenges within OChem is very commonly we imply the hydrogens. Okay? We really only imply them to carbons. So in this particular carbon being a red dot, yes, is a carbon. It only has 1 bond shown, which means there are 3 implied hydrogens. Okay? Which could come to kind of a question that would then bounce based off of your feedback. Okay? That would bounce earlier to stuff we've actually covered in class time. Provide a formula for this. Well, you would identify all of the carbons, and then you would go, okay, well, that has 3 hydrogens. That only has 2 bonds, so that has 2 hydrogens. 3 plus 2 is 5. Plus 1 is 6. Plus another 3 is 9. Plus another... Did I do that math right? Plus another 1 is 10. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. I'm pretty sure I screwed up the counting in there. Okay. But we'd have C, I think we said it was 13, H, 28, assuming I did the hydrogens right. Oh, I actually did. That would then be our formula. You're responsible for acknowledging that. Okay, and that's going to become very important later in the semester because we don't want to show all of the hydrogens. Well, why not?
Because it's time-consuming to draw them all out.
Yeah, it is time-consuming. But did you have to draw that?
No.
You didn't have to draw that, so why do you care if it's time-consuming? So let's take the time, or I'll take the time, show all the hydrogens. Why do you not want to see all the hydrogens drawn on?
It's too much.
Yeah, it looks freaking nasty. There's just way too much going on. That's why we imply those hydrogens. Okay? It is partly a time-consuming thing, but it also clutters our structure up so much. It's very difficult to actually see what's going on within it. So we remove those hydrogens. That becomes one of those implied things that we have to be aware of when looking at a drawing. Does that mean we will always imply hydrogens? No. Sometimes we'll choose to show them. Why? Because our focus is on something else. Okay? So we'll show the hydrogens to maybe remove that added complexity from our overall system. Okay? So there's reasons we would go through and say things or show things for different purposes. You could spin this back to an English class. Okay? You don't write a formal report in an English class with, yo, bro, this is what I'm writing about. That doesn't fly. Your English instructor is going to throw you out the door. Okay? But you could say that to another friend, maybe, depending on your friendships. Okay? And that would be okay. So we will change the context of how we present language and our drawings depending on the scenario that we're trying to deal with. Okay? As students, that's insanely challenging. Okay? I'm going to pick on you a little bit. English second language? Okay? Is it really hard to figure out the context of when you're using different... Yeah! Okay, you didn't grow up with that language. Okay? Whereas the rest of us are first, English first. Okay? We could parse that out. You see someone in a suit, you don't go, yo, bro. Okay, you might say, hello, sir, top of the morning. I don't know, something fancier. Okay? The context changes. But for someone who's learned it as a second language, that context is really hard to nail down. OChem, you're learning a second language. Okay? So you figuring out those contexts is going to be challenging. Worry less about the context and what things are supposed to be there and think through those. Kind of make sense? Thank you. I need to stop picking on you. I'm sorry.
No, you're fine.
Okay. The prefixes with the number of carbons. Okay. Initially, I had it all in order, and I was like, that's going to be dumb. You'll just be able to guess your way through it. So I had to shuffle it up a little bit. So you should know that 1 carbon is meth. You should know that if you see prop, that means 3 carbons. It's okay, you were learning. Hex is 6, 5, pent, 4. That's why we don't call it but, we call it bute. I was like, what? Oh, I get it. Yeah, that's why we don't call it that. We go with bute. Okay.
So is it B-U-T or
It's just B-U-T. So it is still spelled the way as but. So if you think about the lighter fluid, what's the liquid for lighter fluid? What was it? Is it butane?
Isn't there an E in there? Bute?
It's B-U-T-A-N-E.
Oh.
Okay. So the
A
prefix.
makes it-
So you're right. I didn't say anything about the suffix. What comes after that? Why? Because that adds more information. That's another layer to the nomenclature. Is it important? Absolutely. How important is it? Yeah, I'll probably test you on that. Okay, knowing what that suffix is. But at this point, all I wanted to be like, are you getting the bare bones? Do you understand what those prefixes mean? Because those you're going to keep seeing again and again and again and again. You could get away without knowing the suffix for the most part through this semester. Okay? But that prefix is going to be really hard to avoid. Okay? Flipping it all the way up to resonance. For the record, ideally what you're doing is taking notes, not changing your quiz thing.
I just correctly.
That's okay. That's fine.
But I crossed it off.
If we're going to provide the resonance structure for benzene, okay, well, first off, what is resonance talking about? Close. It's not different ways to draw the structure.
The electron?
It's different ways to distribute the electrons. You might say, well, how is that different? Okay. If I go through and I erase that hydrogen and place it over here, okay, number one, I exceed that octet. So let's erase that, and it's going to be weird. Is that neutral? That is neutral. I could do that. Okay, I've changed the location of the electrons. Okay, but really importantly here, I've changed the location of single bond electrons. And what we talked about on Monday was, yes, we can move electrons, but what electrons could we move? 2 types. Say again. Try again, but swap your order now. Instead of saying bonded, no, flip it. Non-bonded electrons you're allowed to move. So if you see a pair of electrons, you can move those. Maybe. There has to be a place to move them. Okay? But you could move those. If we go back to our original structure, do we have non-bonded electrons? No. So we can't move those. Okay? We don't have any to move. Okay? What other electrons are we allowed to move? Multiple bonds. Okay? So anywhere that there's a multiple bond, I could move one set of those electrons. So I could look at this multiple bond and I could say, I want to move that. Whoops, that's an eraser. Let's try that again. I'm going to move that. Okay? So there's my focus. I'm going to look at that pair of electrons and I want to move it. Okay? Where can I move it?
Throw it over.
Okay, trying to follow your MO.
I mean, you can do.
Okay.
You can make it a triple bond somewhere else, or you can make it a double bond somewhere else.
Okay, and so this is again where we have to be careful. Let's just say we made it a triple bond. So I'm going to just minimize things a little bit and just say, boom, we've moved it over here. Actually, I'll do this. Curved arrow, because a curved arrow is saying we want to move those electrons so that I now have a triple bond. To have a triple bond, I need 6 electrons there, right? So I'm going to take these 2 electrons, I'm going to put them here. That's what this drawing means. I don't want to draw the triple bond on this structure. Okay? Why not? Okay? The example I like to use is writing out my name. Okay? So if I asked you to write my name, Okay, we all know it's Mike, theoretically, right? So we start with Mike, M for Mike, and we go, okay. And then we write the I, and then the K, and then the E, and that's how we all write Mike. Right? Is that how you would write out Mike? No, that doesn't make any sense. Okay, you don't put the information on top of it because now it's really confusing as to what you're meaning. Okay? Here, this is a direction. I'm saying this is what I want to do. I want to move those electrons there. What happens when you do that?
You have to move around other stuff.
We'll come back to that. What should the structure look like?
There would be triple bond.
There'd be a triple bond. So if I draw that triple bond there, where did the electrons come from to make that double bond or that triple bond?
You move them.
You moved them from here, which means this red line and this green line represent
The same thing.
the exact same thing. You just wrote directions on top of directions. No one knows what you're talking about. Okay? So if you're going to start providing directions, good, absolutely, 100% provide directions. Redraw. Okay? And that is a challenging concept because we don't want to redraw. Why do we not want to redraw? You actually provided a good answer to that earlier. It's time consuming. Okay? So the choice is yours. Don't redraw and get it wrong, or redraw and have the potential for getting it right. Those are your two choices. Okay? I didn't touch any of the hydrogens, so all the hydrogens are still there. That double bond is still there, and now I have that triple bond. So cool. Does this structure make sense? Okay, why does that not make sense?
Because you have to move, it's too much, you have to move something else.
I need better than too much. I get it.
It's going over your octet, or exceeding your octet.
The carbons, where we put that triple bond, have now exceeded their octet. They can only have 8 electrons around them, or 4 bonds, however you want to count it, and I've got 5. So that doesn't make sense. Okay? So now the question becomes, what do we do with that information? Okay? You started to suggest something that you wanted to do. What did you want to do?
Move another bond.
Move
So
what
it's
bond?
not exceeding. I mean, any of the ones there.
This one?
No, any of the ones that are exceeding.
Okay. So either one of those. Okay, we'll call it green and red.
A hydrogen, or no?
Ooh, can we move the hydrogen? What bonds were we allowed to move?
Non-bonding,
Non-bonding or
bonding,
multiple bonds. Is that hydrogen connected to our structure as a multiple bond?
No.
Nope, so you can't touch the hydrogen.
Okay, so then you can't do that. You can't make a triple bond there.
Okay? Because what are your options? You would have to move either the red or the green away. Okay? And as you try to move them away, all you're going to find is there is only one place that you could potentially move them. Right back to where you started.
Or you could just put them in different places, like the 3 double bonds.
We'll come back to that in a second.
Rotate it, but it's still.
We'll come back to that in a second. So, and that's a really important observation. We have to back off on that just a little bit. Okay? So, let's go back to our initial, I'm fine with this bonded pair of electrons are red. Okay? Can we move them this distance? Okay? This is now going back to understanding of our subatomic particles. Okay? What we're talking about moving is not a bond, but electrons. Are electrons something that can move large distances? As in, can they just exist on their own? No. What's our standard observation for this? How many times have you just walked down the street and just randomly bump into an electron? You're like, how would I know that? Well, where do we find electrons?
Everywhere. Oh, electricity.
Electricity is just electrons. And what happens if you stick a fork in the electrical outlet? You're never supposed to do that. Why?
It'll shock you.
It'll shock you. So do electrons just exist on their own? Do you just walk around and go, ow, I just got shocked? It doesn't happen. Okay, that's because electrons aren't inherently stable on their own. They are bonded to the individual atoms to neutralize that charge. What does that mean about them? Can they travel long distances?
No,
No. What's a long distance?
from one atom to another.
One atom to another is sort of okay. So let's switch atoms to people. Okay, and we'll say the pen, okay, is an electron. Can I transfer my pen to Annie?
Yes.
Yeah. Can I transfer it to Kimball?
Yes.
Really? Kimball, grab the pen.
No.
Why'd you laugh?
Because I have to get up and walk to it.
Ah, so electrons travel very short distance. Can they travel from atom to atom?
If they're close enough together.
Ah, if they're close enough together to effectively create a bond where the electrons can move back and forth. If the atoms are too far away, they can't do that. So defining what that is becomes a challenging question, and that's something that becomes important to us. Okay? If you look at the resonance slide, okay, where it showed the structure of benzene, and I said, hey, you need to draw resonance, I gave you steps and directions on how to do it. We'll flip to that slide in a second. Okay? Our electrons can move, according to that slide, from a non-bonding pair, so on an atom, into a bond. They actually can't go from an atom all the way to another atom. Okay? Because then they have to pass through empty space to do that. They can't do that. But what they could do is go from the atom to the bond, and then they could go from the bond to the atom. Which means if we're going to talk about moving that red bond, we really only get two choices. I can move those electrons to that atom, or I could move the electrons to that atom. That's it. That's all I get. Okay? If I do the green one, what happens? Nothing else changed. And you're like, dude, you got to draw out all this. Yeah, that was part of the conversation earlier, right? We always got to draw it all out. So there's our green structure. We would put a pair of electrons on that carbon. It's going to become negatively charged. We'll have a positive charge on the other carbon. Okay? Do I have to calculate formal charges? Okay, so some people are saying no, cool. So we'll come back to you in a second. How do you calculate formal charge? Because you decided you don't want to do it.
I'm taking the valence minus subtract.
Valence electrons minus number of non-bonding electrons minus number of bonds. Fantastic. Yes, we could go through and do that. Why do you think we don't have to do that?
Isn't that a rule just for Lewis structures?
What is this drawing? It's a Lewis structure.
Yeah.
You're totally right, though. I do not have to calculate formal charge.
Didn't you say, though, that certain resonance structures are better than other ones if you know the charge?
That's a whole different animal. Yes, we'll get to that in a little bit, too. How come I don't have to calculate? Did anybody see me calculate that that was negative and that was positive?
Oh, I see what you're asking.
You didn't, because I just wrote it was negative and positive. Is that just because I'm some magical, mystical being? No. Probably the opposite of that.
Because you took away and gave.
Ooh, what is the meaning of that arrow? I had two electrons in this bond, and I put those two electrons on an atom that had no charge. That atom already owned one of those electrons, so that atom effectively gained a single electron. And if it gains one electron, what becomes of its charge? Negative. I don't have to calculate it. What happened to the other atom? It lost an electron. So it therefore becomes positive because electrons are negatively charged. Neat. What else could I do? So we talked about brute force calculation. We talked about interpreting the drawing. There's one more method. At least one more method. How many bonds is carbon supposed to have? 4. And when it has 4, what's its charge? Neutral. How do you know all that?
Because 4 valence electrons and it has 4 bonds.
That was a lot of thought. How else do you know that?
Because the octet is that.
That's still bringing in a whole bunch of other stuff. You memorized it.
Aren't we not supposed to do that, though?
So this is, again, deciding that balance. When do you memorize versus when do you apply? You will eventually memorize it. There isn't anything you're going to do about it. You're going to do enough practice that you will memorize it. Okay? Should you just sit down and stare at it and be like, I'm going to memorize? No, because now you're wasting your time in the process of memorization as opposed to spending your time on how to apply it. Okay? As you apply it, you will pick up that memorization along the way. Kind of, sort of?
I'm sorry, I got sidetracked.
Nope,
I
go
have
for
a
it.
question, though. So you're saying that is a proper resonance structure?
This is a resonance structure. Yes.
Okay, just because you added in the formal charge?
What I've done is moved electrons. I moved my my multiple bonds.
Had to be satisfied. Like
So, and this becomes a weird gray area, particularly early on in the semester, is that we almost always say, don't draw this as a resonance structure because it's charged. That's bad. We don't want to see charge. But we always want to see that charge later in the semester when we want to talk about how the molecule reacts. So it's a very hard line to straddle between don't show that charge versus you need to see that charge. If this was the only structure that you were able to draw and you could now compare these two, you would say the one in black is better than the one in green.
Yeah.
Yes. If I ask you to draw resonance, I shouldn't be picking a structure in black that results in another charge structure. Because that opens up that can of, well, should I be showing that at all?
Seems really confusing.
Yeah. Does that make sense? Okay. What happens if we did the blue one?
It would be the same thing.
No, it is not the same thing. And this is another kind of hard concept, okay, with resonance that Sydney was extrapolating to later. What happens? The right carbon has gained electrons, it is therefore negative. That top carbon lost electrons, it is therefore positive. Okay, are those the same thing?
No.
Why not?
Well, it's just the charges are different. They're mirroring each other.
Okay, and so this becomes a very challenging question, particularly if we group in the context of the lab activity we did last week. Okay, because that lab activity had you say, whoa, if I could spin, flip, and rotate the molecule to make them identical, I would call them identical. I don't call them a new structure. And so what you might be trying to do is do that with these, to say the green and the blue, okay, are really just flips of each other and therefore are the same thing.
Not the same thing, but they're mirroring.
Resonance, unfortunately, your structure is pinned. Take an anatomy class where you had to dissect an animal and you like pin down the skin so you can poke at that's resonance. Okay? Which means I can't spin, flip, or rotate it, only when discussing resonance. Because what resonance is trying to show is how things can move through the molecule. In one case, we're showing them move to the right. In the other case, we're showing them move to the left. Okay? Yes, if I change my perspective and say, I'm moving to the right, moving to the left, and I go over here, and I say I'm moving to the right, am I moving to the right? Is this your right?
Because you're right.
Therein lies the issue. Okay, which direction are we moving based off of perspective? Resonance locks in, says there is no perspective. It's locked. It don't move it. So if your electrons are moving to the right hand for you, they're moving to the right hand for everybody. And if they're moving to the left, they're moving to the left for everybody. Resonance is a pinned structure.
So then the blue and the green don't count as resonance?
Different question. That's what she's been trying to push on. Okay, are they still resonance? Yes, we moved electrons. Okay, are they as good a resonance structure as the black one?
No.
No.
But why,
No, cool.
can't you just move the bonds and the first, like,
Ah,
why wouldn't that just?
now
be
that
the
I've
first
drawn
one?
this resonance that I don't particularly like, what else could I try to do?
Just like rotate the inner bonds on the inside.
Yeah.
And then
I
it's-
could do more resonance.
Yeah.
This more resonance, I'm not going to look at the multiple bonds now. Where's my focus going to shift to?
Just
Because what you've done isn't a single step resonance, you've done 3.
Oh, and we're just talking about one step?
We want to go through, particularly if you're being asked to provide all of the resonance structures, you're being asked to move through it methodically to address all of them. If you go through and say, oh, I see this one by doing 4 things, you just skipped through 2 or 3 others that you could have gotten credit for that you skipped and now you don't see. So when we do resonance, when we're tasked with the topic of trying to run resonance, we want to go as few steps as humanly possible to address all of the intermediates along the way to say, did we actually cover all of the valid resonance structures? Okay? That's slow. It is, absolutely.
I think I was doing it like in my head, cover the ones that are neutral first.
Yes, okay.
Right.
Which is good.
Yeah.
Okay? But what I'm trying to get you to do is slow down and recognize that you do have those intermediate stages. Okay? If we now look at the blue structure, I guess we could do it for the green one too, but I'm standing next to the blue one. Okay? What's our deal? Should I be looking at moving the multiple bonds, like we did with the black structure, or should I be looking somewhere else?
Well, can't you just work your way all the way down for the entire...
But what am I working all the way down with? That's like telling me, just go downstairs. Okay, I can jump out the window versus going down the stairs versus going down the elevator.
Very original.
What are you moving?
Well, the electrons, but go back to
Ah,
the original.
what electrons? Yes.
Yeah,
What electrons?
from a different bond.
That's my question. Should I be moving the electrons in the bonds now? Or should my focus go somewhere else when I'm now looking at this blue structure? When we talked about the black structure, we said what electrons could we move, and what we established was non-bonding electrons work. There weren't any non-bonding electrons, so we didn't look at non-bonding electrons. What did we look at?
Multiple bonds.
Multiple bonds. Great. We're now looking at the blue structure.
I mean, can't you just repeat those electron moving for other...
So again, what electrons?
Those of the double bond, like say the top left double bond. There
Okay.
between-
Could we move the top left double bond? Yes, that's what I'm asking, is what electrons should we move? No, that's the wrong idea. What electrons should we move? Why do I want to move the non-bonding pair and not the double bonds, the multi-bonds?
Because then the charge goes back
Why do you not like this drawing, but you liked the black drawing?
because of the charge.
Awesome. Charge is inherently bad. It's inherently unstable. When I'm looking at this blue structure and I look at the pi bond, the multiple bond, are those charged? No, which means they are
0.
stable. I don't want to touch them. This non-bonding pair is charged, which means it is unstable. Okay? If you're going to play a game of Jenga, right? It's the block game, right? I got that. Okay? Do you pull the block that is loose, or do you pull the block that sticks? You pull the loose block. The unstable one. My focus will now shift to not looking at the non-bonding pairs, but the multi-bonds. I'm going to look at that non-bonding pair because it is charged. That is the most reactive thing. That's my unstable piece. That is my focus. So I want to move that. Where do I want to move it? As a hint, officially there are 3 options for where you could move it. Say it again.
The closest one?
What is the closest one? And you're saying 1. What's 1? Where can I move non-bonding electrons? When I have electrons on an atom, where are they allowed to move? They have to move close. Well, again, what's our definition of close? Wrong vowel, consonant, consonant, wrong consonant.
One still need electron to satisfy octet.
Okay, so there's an option. You could go through and say, I'm missing an octet on that top carbon, it's positively charged. So where you're saying I want to move those electrons is towards that top carbon. Great. Where do I place those electrons? Can I move the electrons from that atom and give them to that atom?
Wouldn't you just be doing the same thing?
Sort of, but now again, we're working through the logistics of the language. How do we show that? So I see what you're saying. What you're saying is that you're going to end the black structure. I'm okay with that. But I now want, what is the language that I can write down on this paper to signify that that is going to happen?
You're gonna move the non-bonded,
Yes?
the lone guys, to the, you're gonna bring the negative to the positive,
So that?
and you're gonna make it a bond. You're gonna bond
Where-
the unbonded,
Where are electrons to make a bond?
what do you mean?
Like where are they?
Yeah.
In atomic
So,
structure? Like
Can't be atomic, it's got to be molecular. I've got two atoms, and I want to show electrons making the bond between those two atoms. Where do I place the electrons?
In the middle.
in the middle.
In the middle. Where did you just place the electrons?
Not.
Where does that arrow go?
No.
Not in the middle. That's taking the electrons from that atom and putting them on that atom. You have not placed the electrons between the atoms. Because you haven't placed them between the atoms, you haven't made a bond. How do I place the electrons between the atoms? And yes, you can get super irritated at this new arrow that's going to come in.
A single bond.
My arrow needs to show where the electrons need to go. How do I change my arrow?
Didn't you say it just has the one on it? It's
Nope.
not the two.
Because to make the bond, how many electrons do I need?
Oh, you need two.
I still need two, so I still have to move two. Where does my arrow go?
Like to the actual in between bond.
So we'll draw it so you can see it. The arrow should go here. And for those of you looking at it, you're like, that's just a real subtle difference. Is that big of a deal?
Yeah.
Yeah, it's a really big deal. It changes the entire language of the argument. Okay? That's like emphasis on the wrong syllable. People are like, what are you talking about? Okay? All you're doing is changing where you put the emphasis in a word, and that changes people's interpretation of what was said. Okay? Does that matter? Yeah. I mean, the only example I can come up with is coarse cursing, so I'll,
Wouldn't that be moving it two ways, because you have your black structure, that's what you're starting with, right? And then you move the double pair.
I moved
bond,
there,
And then you just moved it back.
so new structure, and now I moved it back. Okay?
But move it down.
But is that two motions? All I've done is ended at the exact same structure I started with.
Yeah, but you still made a move.
I would argue you didn't really make a move. Those electrons, and so this is one of the things that's nice within resonance, we're trying to explain where the electrons exist. These multi-bond electrons are shown best in the bond. But where else do they exist? On that carbon or on that carbon. Those electrons in that multi-bond can shuttle back and forth between those two spots.
Oh.
You haven't really identified a new structure. You've just said, oh, the electrons can move back and forth. Well, yeah, that's kind of what bonds do. They share back and
So
forth.
that wouldn't be a resonance then?
So we can have conversations on whether it's resonance or not. It is a new drawing, so the drawing depiction is technically a resonance contributor.
Okay.
Is it anything that's useful or new or different? Now you run into weird gray
So you
areas.
said there's three possible.
Yes, we addressed one, which took us backwards, not useful. So let's try something new and exciting.
Go down, move it down.
Well,
Okay,
since this-
I love down. Don't go down. Yeah.
Okay.
There's three.
Yes.
There's three double bonds. Wouldn't you basically just do the same thing over and over with each of the bonds?
Our focus is only with that bond. Once we've picked, that's where we start.
It's too far down.
That's all we're addressing. Why do we not look at those other double bonds?
Because there's too many steps ahead, you said, right?
What's most reactive? The negative charge. There's our focus. Our focus is only on this negative charge. Where can that negative charge go? It could go up towards that carbon, reforming our starting bond. That's kind of boring. We want to see something new, exciting, different. One option, let's move it down towards the other carbon. What's the last option? What?
To go,
Because remember, our electrons on the atom can only move through bonds. There was one bond up, one bond down. Yeah, we could go out towards the hydrogen. Okay? Why is going out to the hydrogen a bad idea? So what we're saying is we want to move those electrons to the bond. We'll just show that piece. Why is that a bad idea? Don't look at me like that.
I thought hydrogen was only supposed to have one.
Yeah!
Oh, okay.
Hydrogen can only have one bond. It's the duet rule if you want to get fancy with our language. We can't have more than 2 electrons on hydrogen, which means that structure isn't just like, oh, I don't like it because it's charged. That structure is legit invalid. I can't do that. That's why that one's bad. Okay? We could still use this one as our thought process and be like, is there another way? Is there some way I could fix this? Because I have exceeded its octet. Well, to fix it, I have to move electrons away from the problem. Well, there's the hydrogen exceeded octet. The only electrons I can move are in that multiple bond, and they have to move away from the problem, which means I would need to put those electrons like that. I'm drawing arrows on an invalid structure, which doesn't work. I would have to draw them on the original structure, which means I say my electrons go towards the hydrogen, and simultaneously the electrons go back. What's the net result?
The same thing.
Nothing. Which means
It's not an option.
that was not a valid option.
But are you expecting us to like actually work through those?
Am I
Actually,
expecting you to do that on an exam? No.
Okay.
Where I'm expecting you to do that is with the homework.
Okay, but sometimes
When you
it's
draw it
happening
out.
in my head and I don't draw it out because I just know that.
Okay? And that's okay. I am technically okay with that.
Okay.
Okay? The more you show dead ends and wrong possibilities and dang, I shouldn't have done that as actual notes will set you up. Because if you don't do that, guess when you will?
On the test. But
On the
Just
test.
a question. So I did a lot of erasing on my homework. Can I just?
That's
submit
fine, that's
that
fine.
and
Yeah,
then next
yeah,
week
yeah,
I'll
yeah.
leave it on? Okay.
So what I'm telling you is what you should be doing. You should be making mistakes. You should be drawing things wrong so that you can say why they're wrong, so that you have that evidence for you. Me, I don't need that evidence. I just need to see that you're working through things. And if I see everything that looks perfect, I'm going to look at you and be like, you're going to bomb the hell out of this test. Because what I think you're doing is looking up answers and just drawing answers. You're not going to get anything right on this test. And that's all it's going to be. Be like, I'm sorry, I'm going to judge you a little bit. You're going to bomb. It's not going to work. You need to start doing things wrong on the homework. Okay? So cool. We moved up, boring. We moved to the hydrogen, bad. Let's move down. What happens if we move those electrons down? Where's that arrow ending? Cool, on the bond. Well, I used a green arrow. We'll draw a green structure. What happened to all the hydrogens? Good answer. Absolutely nothing. What happened to the positive charge?
Nothing.
Cool. We're getting into it. What happened to the double bonds?
The 2 that are already there stay the same.
Okay, fair. I knew that one was going to be a little bit tricky. Okay, and what's the new thing?
You add that bond.
Boom. Is this a good structure?
No.
Oh, we got half the class saying yes, half the class saying no. This becomes the challenge. What's wrong with it?
The carbon has too many
that carbon has exceeded its octet. It can only have 4 bonds around it. It's got 5.
And then you still have a positive charge, which you don't want. Or that's
But that positive charge was all the way back here. We weren't even talking about how to address that positive charge here. So I would argue we don't worry about that. We just let that, hopefully that digs itself out later. Okay? But this arrow pushing down now results in a bad octet. When we looked at the hydrogen, what happened? We drew it. We said, oh, hydrogen can't exceed the octet. What did we need to do? We needed to fix that by moving electrons away from the hydrogen. And when we looked at the hydrogen, there was only one set of electrons we could move. That was the set of electrons we moved in. Okay? There was only one multiple bond. We look at this problematic carbon. Does it have more than one multiple bond? Yeah. So I could move that black bond right back. That's boring. That takes us back to blue. Or I recognize that there's another pi bond. I keep using that word. Hopefully we'll get to that today. I can move that multiple bond away from the problem. And because our electrons can only move short distances, we're going to move that multiple bond away from the problem to where?
the
Slow. You say the same thing as her, so help me. We'll move it to the atom.
Oh, 'cause that's
Keep
an
it short
atom.
distance.
Okay.
We'll go to that atom.
So do you have to show that every time? You have to show the electrons going to the atom first and then to the bond?
We'll talk about that in a second too.
Okay.
Okay? Can I show this arrow? Is this a valid thing for me to show?
Does it look like an arrow?
You jerk. I mean, I've been obnoxious as well, so that's fair.
Are you unbonding it?
I'm taking the electrons in that bond and I'm putting them on the carbon. Okay? Is this a valid arrow for me to work from? I'm being intentionally obtuse here.
I feel like it looks like yes.
Why is it wrong?
Well, it doesn't look like you're directly talking about.
The
No.
carbon
Like,
What carbon?
that you're trying to point to, but you're not. Like, do you need to touch it with the arrow?
Okay, is that what you guys, okay.
yeah.
I think I see what you're saying. That point is also that point for the double bond. They're effectively the same spot.
That's kind of what I was trying
So
to
the
Okay.
arrows.
So, and I didn't understand, so through you talking, I can catch up with you now. So yeah, those are effectively the same point. Really what we're looking at is a large dot there. Okay, so do you feel better about it now? Is it good?
Yeah. Why?
But isn't that what you did with the blue one?
Yeah.
When you
Or with the
unbonded?
black one, that's what, with
Yeah, the
that
black
green
one.
arrow, that's what you did.
The blue arrow, even that's
It
the
looks
blue.
exactly the same.
Is because that's different, is this black structure valid?
Yeah.
Yeah.
Is this blue structure valid?
Yeah.
Is this green structure valid?
No.
No. Oh my gosh, because it's not a valid structure, so you
I'm
can throw
drawing
it down.
directions on a thing that doesn't exist. I'm not allowed to do that.
You're just being a trickster today.
I'm trying to point out the holes that you've got to watch out for, which means this is a valid direction. Yes, awesome. I like those instructions. They cannot be drawn on that structure because that structure is invalid. Where do I have to draw that arrow? On the previous drawing, on the blue one. Okay. The result being, I'm going to draw it as purple this time so we can actually see the color of those bonds. Did we touch the double bond on the left? No, so that's still there. Did we touch the carbocation? The positive charge carbon? No, so that's still there. Did we touch the negative charge? Yes, where did we put that negative charge?
On the bottom.
outside. Wait, we're not even involved in valid structure.
Where did we put that pair of electrons?
You bonded.
I bonded it. So I put them on the bond between those. So I now have a double bond there. What happened to the bottom double bond?
You unbonded it.
I unbonded it. So now I have the negative charge there.
Does it matter? Sometimes the bond is like on the outside or does it matter if you draw it on the outside? Or
It doesn't matter. It's a personal preference on how it looks.
Okay.
So even in drawing softwares, you can click them and it'll alternate where it places it depending on how your preference is.
Okay. But same with the rollers, like it doesn't really matter as long as it's.
Yep, as long as they're close to it and theoretically you understand it, that theoretically can become challenging. Okay, so we're gonna delete that green structure. Am I okay getting rid of that one? Because we didn't use it, right? You're not saying yes. It makes me a little nervous erasing it, but I'm gonna get rid of it. Okay, there it is, it's gone. So we went from the black structure to the blue structure. We said they are resonance. We don't like the blue structure because it's charged, but we haven't invalidated any rules. We got to the purple structure from the blue structure, which means they're resonant structures of each other. Again, we may not like it because it's charged, but it's still a valid resonance structure. If blue is resonance of purple and blue is resonance of black, what is black of purple? Should I say it all again? If black and blue are resonance, and blue and purple are resonance, what is the relationship between black and purple?
Purple is another resonance of black.
Awesome. Purple is also resonance of black, which means I should be able to add arrows to my black structure to make my purple structure. I shouldn't have to go through the blue. So this is now getting to, can I string multiple things together? Yes, you can. The question becomes, how do we do it? Okay, well, we'll keep that. Actually, we'll keep that one on the inside. There's our blue on the inside. How do I add arrows to the black structure to describe how I get to the purple structure?
With the color purple.
I should use the color purple. Yes, I like that.
The bottom bond, you're gonna draw an arrow. Or this
That's
one.
fair. I accept. Okay.
But you're gonna do the same thing you did for blue, but you're just gonna put it on the bottom hydrogen. Yeah. No?
If that's all I do, what happened to this top double bond? So remember, the blue arrow is only to get to the blue. What I want to do is now add purple arrows to my black structure to look like purple. And if you only do this purple arrow, what happens to the top double bond?
We're missing a double bond.
It never.
It never moved. Did it move? Yes. So I agree. Purple arrow is good. Yes.
But you need to do
I need another arrow.
another.
So just do it in purple.
I need another purple arrow. Yeah. So tell me what to do.
Like put it by the blue one.
Okay. Just a copy of the blue one?
No, to the
To the
bond.
bond.
Ah, there it is. Why is that curved arrow we just drew so special and different from all the other arrows we've done? Look at all your other curved arrows. What did you do?
Like they're going on the outside.
Atom to bond. Bond to atom. Bond to atom. Bond to atom. We talk about all of the arrows we've already looked at. They only do effectively single jumps. Atom to bond, bond to atom. That's it.
Oh, that one is doing 2 steps.
What is this purple arrow doing?
Double jump.
It's going bond to bond. Okay? This becomes important because that's what allows us to show that we can actually advance another arrow. But that's about it. So we get 3 different types of arrows that we can manipulate. And depending on what we're trying to do, okay, we can choose which one we want to work with. If you're being told to draw as many resonances as possible, you don't want to do this bond to bond, because what you could be doing is skipping past an important intermediate that would allow you to see a branch point where it could resonate one way and another way and another way. So it's all about what you're attempting to do within your structure to allow you to predict how those electrons move. Okay? Kind of, sort of? Do you like the purple structure?
No,
Okay. What do you not like?
it's not stable.
Why is it not stable?
There's negative and positive.
Sweet. Fix it.
Are we just gonna keep moving around and around and around?
Okay, yeah. I'm not trying to do anything tricky. I'm just asking you to tell me what to do.
But then we're just gonna end up back at the black one.
No, we won't.
We won't, because it doesn't shift in space.
Okay,
We're
so
just moving the-
tell me what to do. Stop trying to look at shit that isn't there.
Put them on the, like as a double bond, yeah.
Now what do you want to do? Should I draw that? Too late. Gotta draw it. Jerks. I didn't want to draw it. I mean, you're not jerks. You're learning, for the record. What is problematic with what I just drew, other than I didn't finish it?
The H has the carbon has too many.
I've exceeded the octet. So with this arrow pushing, if you've done resonance enough, hopefully what you see is that when those electrons sweep in to make that double bond, I've got another double bond that's going to be an exceeded octet. So instead of drawing a bad structure, that was the whole fight that we had earlier, right? I can recognize that I need another arrow. What other arrow do I want to add to my purple structure so that I don't make that ugly orange structure that I've now just erased? I need to move electrons away from the problem spot. There's my problem spot. I can move these electrons. That multiple bond. There's my problem spot, my forming problem spot. I want to move these electrons away. Where do I choose to move them away to? Go for it. Okay, I see you smirking because I think you wanted to talk.
Well, where I want to move them's not right yet, but you're just gonna shift them to the carbon as lone pairs,
No.
right? Can you just go with the bond? But you can do that.
You
Let's say
can
you're
absolutely do
skipping-
it.
But you're skipping a step.
We are skipping a step there. So what we would have to do is recognize, do we have a branch point there? If I put the charge there, would I be able to branch those electrons towards that hydrogen? No. Do I need to show that intermediate with the negative charge? No.
Necessarily.
Because I've done the practice to recognize that that's not going to be a branch point, so I can skip that step. I've done the practice to realize that moving this first orange arrow in to make that bond is going to exceed the octet. So I don't want to draw a bad structure. I'm immediately going to fix it with a new arrow. That new arrow, I could decide to draw it to the atom. Perfectly valid. But because I've done the practice, I know that's not a branch point. So I'm going to skip the atom and go immediately to the bond. Why do I want to go immediately to the bond?
Because you know it's gonna work there.
Elaborate. Why is it going to work there?
Because you won't exceed any octets. You won't. I don't know. Because
Okay.
it works.
Cool. Pause. And it works. You may very well have it in your head. And this becomes, I think, the biggest frustration is what you're trying to do is put words, English language, to a system that you've never worked with before. And I'm making you use your words to explain it. And it's insanely frustrating. Tough tiddlywinks. Okay? What happened to that double bond? Or that multi-bond?
You moved it.
I moved it. Where? Up here, right? So I can put it there. Why do I want to move it all the way up there?
So that you don't exceed any octets.
And,
Carbons.
and
Oh,
there it is.
charge.
That positive charge is now going to disappear. It was missing electrons, and what did you just do? You gave it electrons. That positive charge goes away. And we now have this structure in orange. To your statement, because you started to see where this was going, and you were like, but why would I do that? That's exactly the same as the black structure I started with, is it?
No.
No, but it's the same. It's just, you're just moving your...
You're just moving it, except what did we say we cannot do when we're looking at our resonance molecules?
You can't just...
You can't just move them. Those atoms are locked in space.
So you have to
This is 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. In the black structure, I have a double bond between carbon 1 and 2. In the orange structure, I do not. I've moved the electrons around that molecule.
Right, but say like if you just, I'm looking at just the one that's provided. Can you just skip all of the going through all of it and just...
So yeah, when we drew the purple structure, I was like, is there a way that you could skip?
Yeah.
Can you skip from the black to the orange?
I mean, you could just redraw it.
No, you can't just redraw it. You have to have a reason to redraw. What are your instructions that allow you to go from black to orange?
You're asking for the resonance.
Yeah.
The different versions of how that could look.
How do you do that?
And just redraw it. You can't do that? So
You
have to
cannot do that.
Okay, but you could just put arrows on it.
You're now showing why you're able to do that.
Okay.
You don't just say, oh, I can just spin these things and move them around, because you can't always do that. There has to be a reason for it. That reason for it are these instructions telling you that you're allowed to shift it. Okay? That is a critical aspect. You can't just decide, oh, I'm going to move the double bonds. The double bonds have to move because of resonance. That's it.
It's asking you to provide that.
It's not even because that's going to become the next thing. Why do we do all the resonance? This explains where the electrons can move around the molecule. I don't really care necessarily about electrons moving around the molecule. What I care about is where electrons are. Because what can electrons do?
Move.
They can make bonds.
Oh.
So what I care about is now how does that molecule react with something else? Okay? And if I look at this molecule, these electrons aren't locked into this space here. They're moving around. Because they're moving around, does that change their ability to interact with another molecule? Yeah. That now becomes the more important part of OChem. How do we react these molecules and put them together? If I switch this up and now switch to, say, this molecule, it still has a double bond. It's still a 6-membered ring. Would I predict the chemistry of these two structures to be the same? No. They're actually wildly different. Okay? The structure that we just walked through with benzene, those electrons are constantly moving around the ring. The black one, can I just move the double bond to any one of those spots?
Not without changing what
Okay. Yeah, and so if we're thinking resonance, that's carbon 1 and that's carbon 2. There's always a double bond between carbon 1 and 2. I cannot put the double bond between carbon 3 and 4. It's not going to happen. I can rotate it so that carbon 1 and 2 are now over there, okay? But that's not resonance. The chemistry is locked at positions 1 and 2. With benzene, that chemistry is all over the map. What does that mean to reactivity? Well, reactions are based on where electrons are located, right? So electrons have to talk to each other between molecules. If I've got electrons moving all over one molecule, is that going to be more likely to react or less likely to react?
More likely.
Okay? I want to shake hands with somebody. There's my hand to make that interaction, to make that bond. When is it more likely to make that bond? When my hand is right here, or when I'm moving it all around?
Oh, so then no.
The more localized your electrons are, the easier it is to make that reaction. The more they move, the harder it becomes. Resonance is a stabilizing feature for the most part, because it takes your electrons and it scatters them across the molecule. We need to be able to look at a structure and be like, that's got resonance. That's going to change its reactivity. Insanely powerful tool. Is it easy to understand?
No.
Thank you. Right? It is not an easy concept to manipulate. It takes practice to move through all of those systems. Okay? So I can tell you what the steps are. And in fact, I have.
I have a really quick question.
Almost. Here are your steps for resonance. And that struggle that we were dealing with, well, didn't you just move the molecule? What was the very first frickin' instruction? It's pinned. No, you can't move it. That's why the instructions are here. You have to apply those instructions. Application is difficult. All of OChem is application. Expecting to just memorize a fact is why people struggle and why people say OChem is so much memorization. It's so much memorization because you've chosen, either intentionally or through an instructor interference, chosen to ignore that there are rules you need to follow. And if you don't follow those rules, yes, you have to memorize everything. That means if I draw a new structure and I say draw the resonance forms for this, you have to memorize that structure and its resonance. Yep, that's going to be really hard because I can change the structure. Now you got to memorize a new thing. On a test, theoretically, you will have never seen those questions before. You can't memorize the test without having seen the test. So you have to be able to apply those things out. Okay. With that, I will stop. Well, actually, I got 1 minute. Go for it.
So going back to the example you had of just the
Benzene.
black one, and you were like, well, yeah, that one, but then the other little one you drew with just the one single bond, and you were like, that.
Oh,
or,
yes.
sorry, that one double bond. Yes. And you were like, that double bond always has to be between carbon 1 and 2. So like, yeah, you could rotate it and move it down. Is that based on that, like formulas, rules, or because I mean, essentially,
It's based on that structure.
but we moved around the double bonds for benzene.
But
to
why?
be in different places.
Why could we do that? Because when we moved it here, we exceed the octet there.
Because you just keep moving things around until it can work.
There was another multiple bond that allowed me to move. I exceed the octet again.
So then you move it
Another
again.
double bond that allowed me to move. What happens if I try and we'll match, color match, do this? This might actually be particularly challenging for you based off of an earlier statement earlier on in the class.
Because it already has the hydrogens on it, it's already.
Ah.
They're implied hydrogens.
With those implied hydrogens, if I did that move, what happens?
You're going to exceed the octet.
I exceed the octet on this carbon. The only way to fix it is to move those electrons right back to where they came from.
Or you could move it
So you
around
can
and
oscillate
keep
back and
moving
forth
it
here,
all
but that's
the way
about it.
Until, okay,
Kind of, sort of.
yeah.
Hopefully more stable ground.
What is
Rules.
the little, you say atom to bond, and then there's a box.
There's a box.
What is that?
Yeah. Trying to
Oh, you're
get my
talking
thing.
about that box, the example, like what?
Nope. Oh, I have to do slideshow.
Oh,
That's our bond to bond. I want the bond to bond to be a secondary feature, not a primary feature. Okay. Once you understand how to move electrons atom to bond and bond to atom, then yes, whole hog, have fun. Pushing electrons, which I think I saw you have, is going to be jumping immediately into bond to bond.
yeah.
Okay? This puts us a little behind, but I think we'll still be okay. Where we're going to move to, hopefully, next week. There's more memorization stuff there. We've got Vesper, which we'll talk about again a little bit more with the spatial kind of awareness. We already talked about drawing structures and looking at their formulas, the reduced stuff. We've been working through that. So those are mostly review. The models we already did. That's play posit. We do have to review that content. I'm not just leaving you hanging on that for the record. But where I want to get to, this was the big one, is our hybridization theory. So where we're going to start Monday is probably hybridization. Okay.
Monday?
What is today?
Oh, we don't have a day Monday.
No, it's still my dad.
Dang.
That's why you mouthed Wednesday. Okay, so Wednesday. Yeah, Wednesday we'll do that. Oh well. It is what it is. We'll work through it.